Good evening, Hari. So good evening. So good evening, everybody. Like it's 5 o'clock now, so I guess we'll start the problem solving session. I am Naveen Rafael. I am studying in IT Madras right now, and I'm going to be the TA. I'm going to be the TA for Mechatronics. I'm be explaining the concepts for you. So for this problem solving session, I will specifically only look at whatever we have learned in week one. This is mainly because the week two concepts. Firstly, the assignment is still out, and I'm not supposed to be tell. I'm not expected. I'm not supposed to tell you the answer directly. You have to learn it yourself, right? If you have any questions regarding week one, I'll be very. I'll quickly help. I'll quickly answer. If you have questions regarding week two and further, I might defer that question to next week and so on. I can attempt answering, but in case I'm not comfortable with the answer, I might ask you to come see the next lecture next week. So I guess we'll begin now. So we'll first quickly go over uh, the things we have learned in the last 5 days. So the first lecture was mainly an introductory lesson in which he explained the different kinds of mechatronic systems and what exactly a mechatronics means. He gave us timelines, and on top of that, also small introductions of what sensors are, what types of sensors we have, what types of actuators and transducers we have, and things like that. Most of the things in week one, day one, I mean, was mainly definitions. And though a very important thing about week one, sorry, lecture one was the introduction of block diagrams. Is there any question regarding what happened in the first day? Okay, it's fine if there are no questions. The lecture two, Sir showed us 4 examples of different kinds of mechatronic systems. And to be fair, there isn't much extra I can add to that. There isn't any specific questions. Eh, But however, I did see some questions in the forums. Like I prefer answering questions in the actual classes than in the forums. So if the people that asked the questions are here, I request them to ask regarding the. Okay. Just to clarify, I am audible, right? Okay.
Yes, sir.
The
Yeah, it
yeah,
is audible, but yeah, there is a kind of a disturbance, kind of a lagging.
a lag.
Sorry to say, kind of. Yeah, like not
Exactly,
clear,
exactly.
kind, not
I do
clear
not know how to
actually.
avoid the lag. Essentially, I do not think I can fix that. Okay. So the different types of sensors, that's mainly week two stuff, isn't it? Like in week two, sir properly goes through the different kinds of like displacement sensors, acceleration sensors, fluid sensors, and stuff like things like that. So do you? While I can talk a little bit about it, if you want, must realize that this class is a problem solving session. I'm not exactly here to explain everything sir has already explained. I after this I intend on solving specific questions, solving specific questions regarding week one. Okay. The lecture three, in my opinion, has the most important and interesting things. We have a lot of electric circuits, and to be fair, many of the example problems I'll be solving afterwards will be from lecture three. Naturally, we have the definitions of resistors, resistors, capacitors, and so on, and all the different terminologies of what current is, what voltage is, what potentiometers are, what meters are, and all those things. Import. This is a specifically important thing lecture because we introduced Kirchhoff's laws, which you might remember from your 12th plus two and plus one, and that we can solve questions using that. But a stronger thing we've learned, which Sir mentioned in class, is the Norton and Thevenin equivalent circuits. Those are those significantly make several kinds of questions much easier to solve, and at the same time, it it's a new outlook, and I feel like that's one of the first things you will probably learn in this course. Then we also talk a little bit of AC, but the analysis of AC circuits is not that different from DC circuits, except for the consideration of impedance and things like that. The only and secondly, mechatronics does not usually use AC components, so we kind of sideline it. They lectures four and five. Yes, I can give a small brief about Northern equivalent circuit. So, do you know about Thevenin equivalent circuits?
Yes.
I can explain. Okay, so Northern equivalent circuit and Thevenin equivalent are unfairly similar. So Thevenin equivalent circuits tell us that for if you have a very complex circuit, you can simplify it to an equivalent resistor and a voltage source, which will be in series. So, for example, if you have, oh, I can't draw resistors really well, but I can try. Like, this seems complicated. And if you have, so essentially, these are resistors of various resistances, and this will, we can add another voltage source here. So this is a quite complicated circuit, if you ask me. And what Thevenin equivalent circuit the theorem says is that this is equivalent to a Thevenin voltage source and a Thevenin resistor. So the power of, I mean, naturally we'd rather work with this than this. Now, what Norton just says is that this is also equivalent to having a voltage source in parallel with. What Norton says is that this is equivalent to having a voltage source in parallel. Like essentially, Thevenin and Norton are very similar, except that Thevenin says can replace it with a Thevenin uh, voltage source, and Norton says we can replace it with a Norton current source. I personally prefer Thevenin because we like using voltage sources and the when solving using Kirchhoff's laws and the like. But depending on your preferences, you might use the Norton equivalent instead. The idea is simple. Instead of solving a very complicated, instead of solving a very complicated circuit like this, we can simplify it to a Thevenin equivalent, which is equivalent to a Norton equivalent also. Does that explain what I will tell you how to calculate the voltages, the Thevenin voltage and the Thevenin resistance? But yeah, we'll do that in the actual questions.
No, no.
Likewise, I will
What
also
my
explain it
question
for the
was,
Norton.
hello,
Hmm?
am I audible?
Yeah.
So, what my question was like, what's the difference if I'm able to differentiate between a Thevenin circuit and a Norton circuit? So, what would that be?
No, it's what's the
Like, how do I differentiate between using a Thevenin circuit and or a Norton circuit while solving a question?
it depends on your preferences really. Like I personally prefer Thevenin. Some
Okay,
people
so
might
like
like Norton
there's not
instead.
a compulsion. Like if there's this
Yeah, there's no
condition, I need
compulsion.
to
Yeah.
use Norton or
No, there isn't.
okay, sure. Thank you.
Like sometimes the will any will any circuit be combined in the same terminal? I will need to think about that. I mean, surely certain circuits can have the same terminal equivalent, but it need not be the case. We have to solve it out and write the equations, and only then we can say if it's equivalent or not. Like, yeah, it's very possible to have two circuits having the same terminal equivalent. Oh, Utkarsh, I, do you want which part about the terminal equivalent did you not get? Essentially, the primary purpose of terminal equivalent circuit is that it makes the circuit easier to analyze. Like for example, we probably learned about having taking equivalent resistors and then solving questions in class 12. It's essentially like that, but in a slightly higher form. Yeah, don't worry. We'll solve a few, one or two questions on it, and it will hopefully help you. Okay, so lectures 4 and 5 are about semiconductors. As in, we first went about what how the group 14 elements gives rise to other semiconductor branch, and therefore we can have p-type semiconductors and n-type semiconductors. And then with that, we eventually go to and study about diodes. And from diodes, we properly study about transistors and how it's used in different applications. Essentially, among transistors, the important things are how the BJT functions, the junction transistor, and the field effect transistor and MOSFETs work. Those will not have many questions because those don't really have much problems. There are lots of definitions. If you have any questions regarding that, I'll be free to answer. Okay, we'll do the, whatever questions you have about that, we'll do it towards the end. Okay, so I guess we'll first start with the first part I feel is very important. So the energy man concept. What can so the bands cannot be seen in real life. Essentially, the bands are, from what I've understood, scientific modeling of why these things work. Like we can think of the conduction band in terms of perhaps the, I don't want to say quantum orbitals, but yeah, we can say that essentially it's like a massive molecular orbit. But let's not instead of that, another way is, I mean, essentially this is just a mathematical concept and a mathematical model of how the conductors and semiconductors are, and it's surprisingly accurate. Like for example, it the diagrams are fairly trivial. Like it's natural that we have the valence band. If the conduction band overlaps with the valence band, if the conduction band, I'm sorry, I do not know how to fix the lag. Did I lose you anywhere? Or
No, sir. We are not. We are continue actually, but there is no clearance in the voice. Actually, you don't mind if like
yeah, wait, if I speak slower, will that help?
yeah, I think so. Yeah,
Okay, I'm sorry. Like I tend
no,
to speak
and
fast.
then
Yeah,
request. Yeah, I think
yeah,
the mic is should be closer enough so that we can. It will be
Yeah, yeah.
a bit louder.
I'm
Actually,
sorry. I don't have a mic. It's just the
Oh, is it
earphones.
okay? Sorry.
Yeah.
Yeah. Okay.
sound frequency is penetrating to ear.
Yeah. Yeah.
It
Exactly.
is
Yeah. That's
not
what I
very
was saying.
comfortable to ear, sir.
Oh
I'm
no.
Yeah.
sorry.
I think.
Um,
I think
It
I
we
will.
guess
should
from the
clear
next
the.
class onwards,
Yeah.
I'll get another set of earphones and we'll check that.
Yeah, yeah. Okay. See
And this
now,
is
someone
sorry.
speak. Yeah, now someone speak just before you. That was very much clear and audible. Than what your
Oh,
in this session. Yeah.
yeah,
So
yeah.
yeah,
Yeah,
don't
from
mind. Yeah.
next class, I'll bring another pair of earphones also, a headset also perhaps, and we'll
Yeah.
see
Yeah.
how that works. I do not think I can fix this right now. Anyways, we'll go to
Yeah.
the
No
conduction
worries.
band.
Man. Yeah. Yeah. Oh, we can catch. No worries. Thank you. Yeah.
So, say these are the valence band electrons. I mean, we have con- uh, so we have conductors. The So yeah, the energy band concept is just a way to nicely understand. Like it makes sense in reality. Like if the conduction band overlaps with the valence band, that is, the electrons in the valence shell of the metals can e- can easily jump to the conduction band. Then it's a conductor because it does not need any extra energy to start to conduct electricity in the in the thing. However, in case of insulators, there is a massive gap. So you need to give so much energy to ionize to take an electron from the valence shell all the way to the conduction band. You can think of this like how we did molecular orbitals in class 12. If we have done it, like it's not a far-fetched concept. Like essentially, we have an electron here. We have to give it energy to jump, make it go all the way here. The in the case of semiconductors, this jump is less, and because the jump is less, I will come to that towards the end, Harishandran. Chandran. I mean, yeah, that's the last lectures, right? Yeah. So for semiconductors, the gap is less. So it while it takes a little bit of energy, it does not take as much energy in insulators. And because of that, we can even cause this jump happening with sunlight or even a little bit of heat. That's why semiconductors. This is a model to explain why semiconductors change their resistances very easily with temperature and things like that. That's why these are also sometimes called thermistors. Does that the so the energy band concept is essentially just a way to understand better why semiconductors have are at that sweet spot of convenience for us. Yeah, yes, sir. Yeah. So, and then we talk a lot about transistors and the different kinds of transistors. So, I guess we can start solving questions, I guess. Is there any more specific questions about these topics? There were a few questions I had seen in the forum. The issue was they linked to parts of the lectures which don't exist. Like if I click the link, it took me all the way to the end of the video link, and so I was not sure what question was there was. If those people are not here, I guess it's okay. Doesn't matter. We'll go to the question. So the first part I feel is very important are block diagrams. So you can you guys like think for a while and try to draw the block diagrams of these things. A block diagram is essentially have you I the Lego NXT was just an example. And the Lego NXT is clearly a Mechatronics system. You have the controller, you have actuators, you have sensors, and that is the very essence of Mechatronics systems. It's in the end, Lego NXT is a toy. You can use Lego NXT to make different games you want. Like you can make the pot follow a line with using the color sensors and things like that. But in the end, it's just a small toy for Mechaton to study like robotics essentially. So, have you guys understood the concept of block diagrams? I have another small question. Is the screen visible? Is what I'm writing neat and at least legible? Yeah.
We can
Okay.
read that note. Yeah.
Okay. Okay. Like I just want to ask if I have to write bigger things. Okay. Fine. So, is the concept of block diagrams? So can you you can draw block? Okay. For example, the block diagram for an automatic door is going to be super easy, very inconvenience. Like, we'll
So
have hmm?
first of all, there would be a sensor, right? First of all,
uh
there would be a sensor for an
yes,
automatic door.
yes. We will
So
start
it
with
would
the
sense the person.
it will start with a proximity sensor, or
Okay.
and that sensor will check if a person is nearby or not, and the output of that just goes to a motor which opens the door. It can't get easier than this.
Yeah.
Now, this is what you'll call, and this is what Sir's called an open loop system. Because clearly, firstly, there's no loop. Secondly, it's incredibly simple. This is an advantage of open loop systems. Open loops are very simple to conceptualize, and you can quite easily make it. A speed controlled motor, on the other hand, it's not that easy. Because even though you have a mathematical model of the motor, and you know how much current you have to give so that the motor spins at a specific speed, it doesn't always do that. So what we actually do is we have a closed loop control for this. Because of the closed loop control, I'll start at this. Say I'm giving an input velocity. Say the motor is spinning at some arbitrary speed. I don't know what it is, but it's spinning at some arbitrary speed, and I'm measuring it with the with the speed sensor. We'll just call it speed sensor right now. This thing is called a comparator. Essentially, I'm comparing the value from the speed sensor and what input velocity I actually want, and that goes into a controller. We can call this the error, but that it's not so important right now. Essentially, obviously, because this is the measured value. This is the yeah. Okay, so if you okay, never mind. This is the measured value, and this is the input value. So obviously, this is the error. From the controller, it goes to the motor, and the motor makes it spin at some angle, at some speed. So even though we have a mathematical model for the motor, many times just giving that current will not do the trick. There'll be a lot of oscillations and fluctuations with the final velocity of the motor. So if you want a very specific speed control, you need a closed loop system. The Eventually you'll learn about different kinds of controllers. For example, you can use something called a PID controller uh, to set the speed to the motor and stuff like that. But this is the concept of a closed loop system. It, it's slightly more difficult. There is a necessity to use the controller in the thing. So obviously, a closed loop system is more difficult to make than an open loop system. But the closed loop system is much more robust than an open loop system. Like the closed loop system, you're guaranteed that the final velocities will eventually go close to the actual velocity you want. And you can like change the input velocity using some other. You can also change the velocity you want using some other dial, perhaps, and that can change the output. So, closed loop systems are more difficult to study, but they are more robust, which always makes up for the difficulty. So, that's like I feel like these are is the difference between closed loop and open loop systems on this is fine. So, do you guys have any block diagram you want to call? Like, say, do you have any system that you want to analyze? And I'll try my best to come up with a nice block diagram for it. I mean, if not, it's fine for me. I can always make my own. Okay, so okay, a robotic arm is a very good example. So, for a robotic arm, let's say we are interested in position control because most of the time with a robotic arm, you're interested in where exactly the arm goes. Like the speed and angular speed of the arm is secondary. You want it to be precise. Okay, I'm thinking of that kind of robotic arm which goes to specific positions. We can think of the other kind of robotic arm later. So the input is definitely a position. Instead of having this comparator as we did here I'm just going to straight up put a massive controller which takes the position we want, position the arm should go, and the other input is obviously the position the arm is at. Present position of arm. The controller. If you Now this controller, I'm just offloading all the maths to the controller. In general, if you have to solve these kinds of equations, you have to solve massive questions involving Jacobians and things like that. For example, you'll construct a you'll assume that the time taken will be some time t, and therefore you generate the velocity from the controller. You get the velocity of each of the, like, say the robotic arm is like, yeah, it's a very bad robotic arm, but you have joint 1, joint 2, joint 3. So the controller will be able to find the joint velocities for each of the joints, and these can be done with a little bit of Jacobians and things like that. This That's an entire course. There's a course called Dynamics of Serial Manipulators, and that will probably teach you how to generate the joint velocities given the velocity of the end. So now we have that goes to the motors, and from the motors we get the so the sensor in this case is usually the servo motor itself. The most servo motors which are used for robotic for most 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 servo motors have an inbuilt sensor to measure this position of the motor, because otherwise it doesn't work out well. So this sensor will be the servo motor itself. So this will be the very crude block diagram. Unfortunately, most of the manipulation happens in the controller, and the controller is the most interesting part of most mechatronic systems. Like, that's where we spend most of the time. We learn about signals and different controls and things like that. And as you see, this also has to be a closed loop system. And another example for the open loop system would could be a fan, a normal fan you have in our houses. You have a switch, you press the switch, the fan spins. That's a open loop system, because we don't care about the specific speed of the fan. You just care if it's spinning or not.
Okay. So after the motor, that's supposed to be output for the closed loop, isn't it? For example, controller and the motor. So if the required position is not achieved from the robot, that will give the signal through a sensor, and then that will be fine tuning, and then the again that will move to the motors, isn't it? So
Yeah,
the whatever the end is our output, correct?
yeah, yeah. Like, we can. Yeah, you're right. You're right. I was thinking if I had anything to add, but no, yeah, we just said it sufficiently well. That's
Yeah,
right.
okay. Okay, yeah, thank you. Yeah.
Okay, so now we'll go to work circuits again. Oh no, before circuits we have simpler resistance questions. I hope you can solve these kind of questions. I'll give like 5 minutes to solve the first question. If there are any questions regarding the first question, please do ask.
So what's the row of first wire?
For aluminium, it's 2.65 into 10 to the power minus 8.
Okay, thanks.
Yeah. To clarify, these are the diameters of the wire and not some other. These are diameters of the wire. That can be correct. I will. Else, okay. So I'll start solving. So the formula we all know is resistance is equal to rho A by L. I will be a little lazy and I will let's call this R1 and this R2. So we have R1 is equal to rho 1 A1 by L1. R2 is equal to rho 2 A2 by L2. Since the lengths are the same, let's okay, I'll write it. So for the resistance of the first y, we get 2.65 into 10 power minus 8 into well the cross sectional area of the wire. The cross sectional area of the wire will be
Excuse me.
pi. Yes.
So I guess you wrote the formula inverse, like you wrote the wrong formula. R
Yes,
is
sir.
equals to
I'm
rho
sorry.
L
I'm
by
sorry.
A.
I'm sorry.
Yes, sir.
I'm sorry. That yeah. I
Yeah.
Yes,
thanks
sir.
for
So that
reminding
would
me.
have given the wrong answer there.
No one saw this. Yeah. So we have yeah, and the denominator will be pi into 8.3 by 2 whole squared to 10 power minus 3 squared. And when you put this into a calculator, you get point 0.5 into 10 power minus 3 squared. I hope I've got the I've written the value correctly. I got 9.79 into 10 to the power minus 5. I hope you got the same answer. Four point five, 4.5, 10 power minus 3, close bracket square. Yep. So yeah, we do get. I will check these numbers again using my own calculator, but I'm fairly certain these are right. Okay, so that's how you. It's not a difficult question. It's just an application of a formula you should have would have studied in class 12. The thing is, we are engineers and we don't actually get things these nicely. Like 8.3, we can't exactly have something that is exactly 8.3 millimeters. We always have some tolerance of error and things like that. And as engineers, we must understand how to choose the resistors correctly. And that is why the resistance color codes are kind of important. Like in the end, what we actually do is to go to the shop and specify the uh, resistors in this format. Like we'll say some 23 into 10 power 5 ohm resistor, and the shop owner will give you a red, orange, green resistor, and depending on your tolerance, you'll select the correct thing. Like if you're building your own mechatronic system, it might be useful for you to know the color codes, but it's not incredibly necessary otherwise. I'm specifying this because it's very easy for people to give you questions based on this. Like they can show you a picture of a resistor and ask you what the resistance is. And for that, you have to just remember what each of the color codes stand for. That's a that's a common question which I've seen at least 2 times. I hope I'm clear. Okay, carrying on. The next question will be, it's a simple question. Like I will be solving this question in multiple ways to properly understand all the different kinds of ways we have learned in this course. The question essentially right now is, what is this resistance R? Given that this is an ideal ammeter, and it's reading 1 ampere resistor. Yes, it's reading 1 ampere current, and given this system, find the value of this R.
Excuse me.
25 by 16.
That's not right. Unless I've made a mistake when making the question, but I'm fairly certain that's not right.
It's
Okay.
4 ohms, sir.
Yes, that's right.
It's 4. Yes, sir.
I made the question so that it would be 4 hours. So yeah, the answer is 4 hours, but yeah, the naturally the easiest way to approach this question would be to use what we have done in class 12.
Yes,
The
sir.
series is in parallel,
That's
na
what I
sir.
have done.
That's why
Yes,
we are getting
for
four.
the four and five, four and this thing are in parallel. So the four and R are in parallel. So we can replace this with an R equivalent, and the R equivalent will be, if you are using a proper formula, we'll get Req is equal to 1 by 4 plus 1 by R, and with a little bit of algebra, we can get R equivalent is equal to 4 plus R by 4R. Now, if you so then we can do it again, but this time with series resistance, and it will the thing will simplify to Req. This is 5 volt. Sum of these two, 4 plus R by 4R plus 3 is equal. Call this Req2 and this is Req1. I did make a mistake. We know that the current is 1 ampere. So we have V is equal to IR, famous equation. So that's phi is equal to I is 1, 1 multiplied by 4 plus 13R by 4R. So when we, since that, so this simplifies to 20R. Oh no, give me a second. I'm sorry. R equivalent is 4R by 4 plus R. I mean, when you add this, you get 4 plus R by 4R here. And this is inverse. So,
Yeah, one reverse. Yeah.
and that simplifies to 7R plus 12 by 4 plus R. So when you cross multiply, we get 20 plus 5R is equal to 7R plus 12. Solving this linear equation, we get R is equal to 4. Well, this is one way of solving it. The other way, I feel like this is a way we can properly study Arc-Thevenin, the Arc-Thevenin equivalent circuit also. So we will take all this. That's one way. Let's do it using the Arc-Thevenin. So let us consider, okay, let's find the Thevenin equivalent of this part, which shouldn't be too difficult. That is the if you find the Thevenin equivalent of this, this entire thing becomes V Thevenin R Thevenin joined with R and here. Wait. Okay, we'll solve it the other way around. In this sense, I'm sorry. I had a different idea in mind. I changed in the last moment. So we know that this is a 4 ohm resistor. We just found there's a 4 ohm resistor. Let's see that whether using arc Thevenin, if you're using the Thevenin approach, that we okay, because this is a 4 ohm resistor, we know that this is a both of these are 4 ohm resistors. So naturally, the current through both of these should be the same. That means if you do normal calculations, you will find that this half ampere for flowing here and another half flowing here. I was going to show you that if you're using the arc Thevenin approach, I mean using the Thevenin equivalent approach, we can get the same thing. That is, if you find we can write this as V Thevenin. Okay, so using the other approach, we had using the normal approach, we found that the resistance is 4. This resistor. We found that this is 4, right? If this is 4 and this is 4 and we have an 1 ampere flow flowing through the entire through the circuit, what does these are parallel resistors. Parallel resistors will have the parallel resistors will try to share current, and how much they are sharing current will depend on how much resistor there are. So, for example, if you have 10 ohm here and 20 ohm here, then twice the current will go here, and if a current if okay if 1 ampere flows in this branch, then 2 amperes will flow here, because that's how it works in parallel, right? In parallel, what happens? In parallel, we have that the voltages are common at the end. If the voltages are common at the end, and we have V is equal to IR, that means in this branch, the V is this thing, the current is something, and the resistance is 20. In this branch, the V is the same, the I is something, but the resistance is 10. Naturally, this current has to be the current in this branch has to be double the current in this branch. That's how the when we found that Req is equal to 1 by R plus 1 by R, 1 by R1 plus 1 by R2, we used this principle. If you want, I can. So So I'll be deriving the equivalent resistance for for a parallel set of resistance right now. What we have is, say you have two parallel resistors R1 and R2, and a current I is flowing through them. Now we can use Kirchhoff's current law, and we have I1 going here and I2 going here. This is a junction. According to Kirchhoff's current law, the amount of current flowing into the junction has to be the same as the amount of current flowing out of the junction. So we have I going inside and I1 and I2 going out. So we have our first equation. I1, the net voltage drop across the entire system is V. Naturally, because uh, the voltage drop does not depend on the path the current takes. Voltage drop always just depends on a certain end position. That's why we have voltages. When we talk about potential and potential energy, we talk about exact positions, right? So the path the current takes does not matter. So we have two more equations now. The first equation is the current I1 goes through R1, and that's equal to V. That is, V is equal to I1 R1. Likewise, we also have V is equal to I2 R2, because we have I2 going through here and I1 going through here. Yes? That is, I1 is equal to V by R1 and I2 is equal to V by R2. This means that I is equal to V by R1 plus V by R2. This is equal to V into 1 by R1 plus 1 by R2. But we know the voltage current relationship is supposed to be V is equal to IR. We want to write this as V is equal to I into R equivalent. So if you are bringing this side, what we'll get is I into R1 plus 1 by R2 whole inverse is equal to R is equal to V. That means that R equivalent inverse is this term. Right? So the entire premise is this thing. The voltage drop across the parallel set of parallel resistors is the same, and the current through each branch will depend on what the resistors are. So if the resistors are equal, then naturally the current will split equally. So in this question, I was saying that we have 4 ohm and 4 ohm are in parallel, and because the 4 ohms are in parallel, the current through them will be the same. Here we have 1 ohm, 1 ampere current flowing, and if the current flowing through these two are the same, then it has to be a 0.5 here and a 0.5 here. Right? Does that make sense, Purushottam? I guess I went first. So I was saying that. Okay, I'm sorry. I assumed that this was trivial, but never mind. So if you solve the equation again, we can see that there's a half ampere current flowing through here using a normal analysis we did. I was going to say, let us see if we'll get the same thing if we do arc Thevenin approach. So if you're going to do the arc Thevenin approach, first we must find two things. We must find the Thevenin equivalent. Okay. So the idea right now is we are writing this as VTH, RTH, 4. As you can see where this is from this. So where this thing is from this. This is the very premise of how how to use the Thevenin equivalent circuits. So to find VTH, okay, finding RTH is easier. RTH is you find RTH by drawing the same circuit but removing every voltage source and replacing it with a wire. So it will look like and we have to find the equivalent resistor across this. The equivalent resistance of this is naturally using the these are clearly resistors in parallel. So the equivalent resistor RTH is just 12/7. For the VTH, we have to have the voltage source back here again, and we have to find what the voltage difference between A and B is. This is something Sir explained in class. This is a this is a potential divider. So we have VTH is 5 multiplied by 4/7. You can see this is a voltage divider in a sense. It follows the same. It's exactly what the diagram is. Did the voltage divider part make sense? Otherwise, we can solve this normally also. But is there anyone who got confused about the voltage divider part?
So where you get 4/7, sir? Not getting, sir. This 4/7.
So the formula for the voltage divider was the voltage across this voltage across the voltage across this will be R by the voltage across the entire thing. So 3 plus 4. Because we are we these are resistors in parallel. Sorry, these are right now in here. These are resistors in parallel. Right now here these are resistors in series. 3 and 4 are in series. Like we are even though we are trying to find it at A and B. Right now this is all we're looking at. This is easy. The purpose of the Thevenin equivalent circuit is to make it easier for us to analyze. And this is an easier circuit to analyze. So when you're analyzing this circuit, we can easily see that 3 and 4 are in series. 5 is in 5 is the voltage source, and therefore the net current will be 5/12, and the voltage across the 4 ohm resistor will be that multiplied by 4. Sorry, 5/7. Wait. I'm talking about this. I'm straight up using this equation. Like you can see how this is exactly the same thing as this. There's 5, 3, and 4, and here we have 5, 3, and 4, and we want to find VR2. Instead of using the equations directly, we can always derive it. But I mean, the point of
Yeah.
equations is to solve it quickly, right? I hope that made sense. How this is a voltage divider. Okay. Anyways, so this is a voltage divider. You can, by the way, these are recorded, so you can always come back and see what I've done. So what we have is 4, 5, 7. So this circuit will now look like this circuit will now look like VTH is 20 by 7, RTH is 12 by 7, and the outside resistor is 4. These are clearly resistors in series. So if you are going to solve for this, we get the equivalent resistor here is 12 by 7 plus 4, which is equal to 28, 40 by 7. I will copy this into the next page. V is equal to IR. So 20 by 7 is equal to I multiplied by 40 by 7. Clearly, solution is I is equal to half. That means in this circuit, we can get that we see that the current is 0. We get that the current in this arm of the circuit is 0.5 amperes, which is in accordance to what we expected from the actual thing. Now, another concept which I've probably seen before is the Wheatstone bridge, and I thought that it would be very interesting for us to study the Wheatstone bridge from the what's that from the Thevenin approach. Oh, I'll quickly talk about the Norton approach also. Like personally, I prefer Thevenin, but Norton is not that different. Essentially, for Norton, instead of putting it like this, we have to put a, a current source. I'll put it here. The the Norton resistor will be the same as the Thevenin resistor. So that part is easy. The Norton current source is actually just the Thevenin voltage source VTH divided by 12 by 7 divided by RTH, and you will get the same equations. So give me a second. I'm sorry, I'm having a uh, small confusion. I'll clarify this both in the notes and in next week's class if necessary. But if I remember distinctly that ITH is equal to VTH by RTH, but that does not make so much sense right now, and I'll clarify this later. In the end, all of these are just formulae that you kind of expect you to remember. But with practice, it'll be very it'll make sense. So as I was saying, I thought it'd be very interesting for us to solve the look at the Wheatstone bridge in terms of the we in see the equivalent circuit for the Wheatstone bridge. Normally, this is how we see the Wheatstone bridge, and the important part about the Wheatstone bridge is that R1 by R3 is equal to R2 by R4. If this condition is satisfied, if this condition is satisfied, then points A and B will have no potential difference. So if you have a resistor here, then that no current will flow through the resistor which is kept here. Like so say I have a resistor here. According to the Wheatstone principle, the as long as this condition is satisfied, there is no current across the resistor R5. Note that you cannot place another voltage source here and expect the things to the equations to be the same, because naturally it won't be the same. This is a different system altogether. But we can analyze this in terms of uh, Thevenin equivalent circuits. So first, let's find the Thevenin equivalent resistor. One way which I recommend under, doing this is by opening up the circuit. That is, let's start with A here and redrawing the circuit so that B is on the other end. A goes and splits into two wires. From A, it goes and splits into two wires, which goes to R1 and R3. R3 splits into two wires also, going to R4, and R4 joins with something and goes to B. The other part of R3 splits into the voltage source, and yeah, and that's connected here, and we have this. Could have gone that slightly deeper. So, yeah. But since we are trying to find the Thevenin equivalent, since we are trying to find the Thevenin equivalent resistor, we can replace the V with a close line. So whenever you're solving this, you should always replace, when you're solving for the arc Thevenin, you should replace every voltage sources with a closed closed wire. And this is a very simple system. This is essentially two wires in series. A couple of things in parallel and a couple of things in series. So we can simplify this as we have A split. This is R1 R3 by R1 plus R3. This is, I mean, these are in parallel and this is in parallel, and these are in parallel and these are in parallel. So we can use the equations of the parallel resistors, and we can just add them and we get a kind of ugly equation for R Thevenin. R Thevenin is the sum of these two. Now, if you're finding the equivalent resistor, we should first analyze the system. So we'll the same setup. One, two, four, three. So we can ignore these things first, and we just solve this system. This system is not too painful to solve. So for this, we can solve it using we'll solve this using the normal KVL approach. So let's assume this is ground. Then this has potential V. Fine. This is the easiest way to solve. So let's say there's a current I1 in this branch and current I2 in this branch. The current I1 multiplied by R1 plus R3 is equal to V, because the voltage drop across R1 and R3 is same as the voltage drop from this point to this point. So we get this equation. Likewise, we get I2 into R2 plus R4 is equal to V. So what will be the voltage at this point? The voltage at that point, if you ignore this section, this is again another voltage divider. So the voltage at this point will be R3 by R1 plus R3 into V. The voltage at this point will be we can consider this section as a potential divider, because all we have is a current and two resistors. So to find the voltage we are finding this voltage, the voltage between these 2 points, and so that's just the application of the voltage divider formula. Similarly, VB will be equal to R4 by R2 plus R4 into V. Now, let's call this K. R1 by R3 is equal to R2 by R4, which is equal to K. That means R1 is equal to K into R3, and R2 is equal to K into R4. Okay? And substitute those here. That means we have VA is R3 by K into R3 plus R3 into V. R3 is common everywhere. So we can simplify this as V by 1 plus K. Likewise, VB can be simple because R2 is equal to R4 into K, we get R4 into V by K into R4 plus R4. Since R4 gets cancelled, we get V by 1 plus K. That means the potential at B and the potential at A are the same. If the potential at V and potential at A are the same, that means V AB, the potential difference across AB is equal to 0. Because what is potential difference? Potential difference is difference of potential, right? So we get this is equal to 0. That means under the sorry, give me a second. Under the Wheatstone bridge condition, we get that the potential across these 2 points will always be 0. That means in the Thevenin circuit, we get a 0 voltage, and an ugly off Thevenin. We get 0 voltage, an ugly off Thevenin, and the remainder of the circuit. So we see that we can use the Norton, we can use the Thevenin equivalence circuit to study this better. Because if I had to solve this, if I had to solve this properly, if I had to solve this properly using KVL, say we have I1 going here, say I is the total current, and there's I1 going in this. I changed, sorry. I1 here, I2 here, I5 here, I3 here, I4 here. That's a lot of currents to keep track. And you have to write a lot of equations. I is equal to I1 plus I2. I1 is equal to I5 plus I3. And that this will make the analysis incredibly tedious. So, but instead, if we had used the Thevenin equivalent circuit and found the Thevenin equivalent circuit about these 2 points, we'll reduce the system into putting this R5 here, and we found that there's a zero. We found that the V Thevenin will be zero. That means if V Thevenin is zero, that means there's no voltage source in that in that thing, and therefore we see that under the balanced Wheatstone bridge conditions, there is no current across the AB gap. I understand this is a slightly convoluted way of approaching this, but I felt like the Wheatstone bridge is a very fundamental part about many of the things we do in measurements in sensors and things like that. That I felt like we can study this better using the Norton with the Thevenin principles also. I realize this is a little convoluted. Okay, so that will almost conclude the circuits part. There's nothing extra I'm going to touch in AC, because in AC all you have to learn is about the impedances and things like that. And Sir has not given you the formula, so I don't expect that you're expected to know those formula either. Secondly, yeah, all you're given are these things, which frequency is 1 by time period is a formula everyone knows. Yeah, so he has only given this much, and I was frankly, so I thought it's not necessary that we have to study these perfectly. But if you had to, you have to start by finding the impedances. So the impedance of a resistor is, well, the same thing. The impedance of a capacitor is the capacitance divided Z R is equal to 3. ZC, which is the impedance of the capacitor, is the capacitance divided by 2 pi I frequency. Oh, give me a second. Yeah, the CS example. I'm sorry. So once we have these are specifically called reactances. So now you find the net reactance using the normal. After this is all normal analysis. So you find the so the net reactance here will be ZR plus ZL, which is 3 plus I omega is 3000. So 3000 into L, that is 1500. This is 1 by I into 3000 into 0.2 microfarad, which is which is 1.666 1666.66 minus I minus, okay. And now we have the net impedance of this is this, the net impedance of this is this, and these are clearly in parallel. So you can have the same equations as before. So 1 by 3 plus 1500 I plus 1 by minus 1 by 66666.6 I 1 by R 1 by Z equivalent is equal to this. And you can find the equivalent impedance of the entire thing, and then you add the resistance. It's essentially the same equations. The only difference is we are now considering current, resistors, and everything in the complex plane, because that makes the maths much nicer. Even though it's very frightening in the beginning, all of these make the math much nicer when you solve it properly. The other way, you can theoretically solve the entire thing using KVL and KCL. However, those will give you differential equations, and we really don't want to be touching differential equations now. I mean, solving differential equations is fine, but it's always nice if we don't have to, right? Because if you're solving this using complex numbers, it's just essentially the same algebraic solution. So yes, that concludes the AC analysis. Regarding the for semiconductors and transistors, there were hardly any major equations other than these. But these are just things you know, and there are not many. I was not able to make some nice questions regarding these. I'm sorry, and even the material did not give us decent questions, right? So, are there any questions regarding? One person had a question regarding FETs and bipolar. Okay, they are essentially different transistors in the first place. Sir has given us proper like like they are essentially different transistors. They are made in different ways. They have different purposes and things like that. From what I've heard, is most people use FETs more often than bipolar now. FETs have evidently you can see FETs have better properties. Not necessarily better properties, but FETs are more convenient to use apparently. Is there any further questions about? Like, I don't have many questions regarding FETs, and because there are a dirt of formulae. Like the Darlington transistor obviously has a gain of over of 100,000, because naturally the the two transistors will each have a gain of 100 each, and therefore the net gain is 100 times 100, which is 10,000. There are questions I've seen regard with diodes which go in the form that, say you have an AC circuit. Like this is a half bridge rectifier with this is a half bridge rectifier with the capacitance, and that will help in voltage regulation. In regulation, there's also the Zener diodes, but those also tho- those are just components which you have, and you know the properties of, so you can use them in the specific places. Transistors are used as switches, as explained in the first few slides. You can use a transistor as a switch, as evidenced by this section. Essentially, if you provide a current here, if you don't provide a current here, the voltage across VCE will be won't allow current to pass through. Therefore, it acts like a switch. I, I prefer if people ask questions regarding this. Otherwise, you can just solve one of those questions. Otherwise, you can just solve a question on northern equivalent circuits, I guess. Give me a second. So we can just go haywire on the question. Oh, otherwise, I can show other methods you can solve the method I solved here, in which I used potentials. Is that familiar to most of you? Otherwise, I can explain that. Like, potential difference is essentially a difference of potential, right? So one way which really like solving these questions is to assume a potential at different points. So say I have the previous circuit. I assume that the potential at this point is zero. Therefore, because we know the potential of the source is V, the potential at this point will be capital V. The potential at these points will depend on what the current flowing in these loops are. The current flowing in this branch we found to be we had found the current to be I1, which is I1 is equal to the current flowing through this branch was is this. So if this is at position, if this point has potential V, and let's say this point has potential X, we know V minus X. That's a potential difference across the resistor, and that is the I into R1, R3, R2, R4. So if the potential here is X, as I said, so this will V minus X is the potential difference across R1, and that is I1 into R1, which is equal to V minus X is equal to V by R1 plus R3 into R1. If you rearrange a bit, you will get X is equal to V into R3 by R1 plus R3. This is another way you can solve these kind of questions. There is also an absolutely amazing method to solve these kind of questions using matrices, but I'm not very comfortable using that method because it's usually easy to just solve this. From the next class onwards, I think I'll get more questions. I ran out of questions fairly quickly. I thought the class will be a little long. Okay. Yeah. Say we have a resistor like oh, we have a more complicated question. So we'll call this 5, 10, 5, 5 ohm, 5, 2 ohm, 4 ohm, 8 ohm. So, and we say we want to find the current in here. So the main way we solve this is we can okay, let's say potential here is 0. That means we have the potential here to be 5, the potential here to be 10, and the potential here to be 5 again. But we have three branches of current. That is, let's call the current here I1, the current here I2, and the current here I3. And we know the potential at this point is this same. We call it X. So we have X. Is someone speaking? No, right? Okay, never mind. So the potential difference across this, the potential difference across this resistor is X minus 5. And we know this is equal to 2 into I1. The potential difference across this resistor is X minus 10. And that gives us 4 into I2. The potential across the last resistor will be x minus 5 again because the potential here is 5, and this is equal to 8 into I3. But if you look here, there are three equations. There are only three equations, but there are four unknowns. X is an unknown, I1, I2, and I3 are also unknowns. Fortunately, we have one more equation in terms of the KCL. We, we know that this is a junction, and this sum of currents going inside is equal to the sum of currents going outside. At this junction, however, there's no current going outside. Therefore, the sum of all the three, I1 plus I2 plus I3, this has to be equal to 0. This means that one of these currents is negative, but that just means that the current is flowing the opposite direction. So this gives us three equations and four unknowns. Four equations and four unknowns, and this can be solved using any linear using any method. Like personally, I would just drop this into MATLAB because we can write this in matrix form. So these kind of equations can be solved easily using MATLAB. If you're a little confused how I got this, I wrote all of this in uh, the linear form. So that will be minus 2I1 plus 0I2 plus 0I3 plus x is equal to 5. 0I1 plus minus 4I2 plus 0I3 plus x is equal to 10, and so on. So this gives us four equations and four unknowns on this side, and we can generate the matrices by looking at the coefficients of each of the terms. This is a normal matrix matrix equation of the form A x is equal to B. So MATLAB, since we can find the inverse of this matrix, we can very easily find what I1, I2, I3, and x are. I don't have MATLAB nearby, so I can't solve it. We can obviously also solve this using normal substitution methods. So, so we have x is equal to 2. We get I1 is equal to x minus 5 by 2. I2 is equal to x minus 10 by 4. I3 is equal to x minus 5 by 8. Substituting all in the last equation, we get x minus 5 by 2 plus x minus 5 by 2 plus x minus 10 by 4 plus x minus 5 by 8 is equal to 0. We can solve for x here, and we'll get x is equal to 45 by 7. approximately 6.5. That means if x is 6.5, 45 by 7, that means the last equation, x minus 5 is equal to 8i3. Sorry, the second equation, x minus 10 is equal to 4i2. The x is less than the 10. That means I2 is that means I2 will be negative. So I got the direction of I2 wrong here. I2 would actually be in this direction. So we'll have a current I1, uh, a positive current I1, positive current I3, and both of them will merge here and go to I2 here. So this is the other way you solve this using a mixture of both assigning potentials and a little bit of finding KVL. Sorry, KCL. Solving this manually like this will give you the same equation as if you are solving using the MATLAB method, as I said. Well, we can go ham and solve this using the Norton equivalent, uh, using Norton theorems. Sorry, Thevenin theorem. We'll get take take this region to be the take this to be the Thevenin circuit. So we have, and this is point A and this is point B. So what the thing will look like is this is 5, this is 5, this is 2, this is 8. Note that these two will be these two, these two will be these two. You can see how they are essentially the same. So RTH will be R Thevenin. Well, remember, when you're calculating R Thevenin, you replace all the voltage sources with closed loops, closed wires. So RTH is very easy to calculate. Well, it's just 1 by 2 plus 1 by 8 plus 5, 8 by 5. And for BTH, you have to solve it properly. For VTH, we get say the current is I. I am getting the current to be 0, and therefore I'm getting the current to be 0, and that means that VTH is 0. you can so the analysis I did was I assume this is zero. That means this is 5 and this is 5. The potentials here are 5. Say the potential here is x. So we have 5 minus 5 x minus 5 is equal to I into 8, and x minus 5 is equal to I into 2, and that implies that I is equal to 0. And that means x is equal to that means x is equal to 5. That means the potential at so we get VTH is equal to 5. So this entire analysis simplifies this entire circuit simplifies to this. We have a VTH of 5, Thevenin's resistor of 8.8 and a half, a current source current of 10. I mean, the remaining part of the remaining part of this, and this we can find the current for this the same way as we always do. So, and once again, you can see that solving this is kind of easier than solving the entire thing here. So 0, this is 5, this is 10, this is x. X minus 5 is equal to 855 into I. X minus 10 is equal to 4 into I. Two equations, two unknowns, and you can solve for this in short amount of time. I've worked a lot more with circuits and equations, and that's why I'm very I'm a connoisseur of saying use them in equivalent circuits, and therefore I like solving these methods. If anyone had a question regarding transistors, I'm willing to explain, but I do not know how to generate questions for this. Many of these things are essentially conceptual stuff, and FATs are very useful in real life. And the concept is kind of intuitive because of the way the reverse voltage and things like that work. If you have P and N junctions, if you have P-type semiconductor surrounded by N-type semiconductor, it generates a region of it generates a region of a depletion zone in between. That N-type semiconductors can conduct electricity. P-type semiconductors can also conduct electricity. But because of the if you apply a greater voltage, the depletion zone increases or decreases, and that affects the amount of that increases the channel. That increases the distance. That increases the region of N-type semiconductor here, and because that changes the amount of N-type semiconductor here, you can increase and decrease the current here depending on the voltage application at the gates. So, how do you guys find the lectures? I can't explain. Oh, like one of you had asked a question about getting marks for closed instead of closed loop, or getting marks for closed instead of closed, because the answer key says we need closed loop control instead of close. Personally, I feel this is a slight English error because close and closed mean slightly different things. Close means in close proximity, as in two things are nearby. But closed loop means that the thing is closed. When you say the door is closed, it doesn't mean that the door is near something else. Closed and closed are slightly different. I do not, I can ask my senior about whether you can get marks, but I can't guarantee it.
Can you clarify that FET and this bipolar differentiate?
I pointed it out earlier, right?
Yeah.
Essentially, they're completely different. Uh, they are completely different technologies. FETs are FETs are made using this specific arrangement, as in you have an N-type semiconductor and you have two regions of P-type semiconductors in it, and this is done by methods like etching and things like that. And this is this is the N-channel FET. Uh, the normal okay, doesn't matter. The normal trans the normal BJTs are in this form. So they have they have different architecture in the first place. Secondly, because of different architecture, FETs have are kind of nicer than BPT, BJTs. Like one concept which is pretty clear is that FETs definitely are don't have a specific direction. You can have the source and drain interchanged, but in the BJTs, emitters and collectors have different sizes, and therefore we can you can't swap the size. You can't swap the emitter and collector around. So they are different. They're different technologies in the first place. I mean, they have the same effect in a sense. They have similar effects in a sense, but that doesn't mean that I feel like there's a lot of differences between them. They are transistors in the name essentially because we can control voltage and current using voltage and
Okay.
current control using other. Yes.
Here, how is impacting low input and high input and current and voltage will be vary.
So in the case of FETs, you apply a volt when you apply a voltage, the depletion zone changes, and this change in depletion zone will affect the current that's passing in this direction. So well, say there's a current going in here. The current going there depends on the width of this depends on this width. If this width is less, then the less current will flow. And if the width is more, naturally more current will flow. That this width depends on how depends on how much voltage is applied. If voltage is applied here and this is forward bias, then the width increases. If the if it's reverse bias, then this width will reduce. So FETs definitely are voltage driven. FETs are clearly voltage driven. On the other hand, for BJTs, the when current flows here, the depletion zone here depends on how much current is flowing here. More current that flows here, the depletion zone here changes, and therefore the what's that thing called? The depletion zone here changes, and therefore it can act as a switch and so on. I am not familiar with why they are calling it as a low impedance and high impedance. I'm not certain why it's called low impedance and high impedance. Look this up and get back to you.
Yeah, in this lecture, this FET is having the most part. So metal oxide that will be give that more isolation part.
Yeah, I agree. Like we know that the MOSFET has a high, high impedance, higher impedance than FET, but I'm not certain why the input impedance of
Yeah,
yeah, I'm
that's
not
what.
certain why the input impedance of FET is greater than BJTs. So yes, that would if there aren't any more questions, we can conclude the meeting. I'll stay around for a while more, but you guys can leave. If there are any questions, you can feel free to ask. Yeah,
Yeah,
preferably in the circuit section.
can you
Yes.
give example where that exactly the FET was FET and this can be used our application?
So FE, I do not know if this is specifically used in this case, but being able to switch between states is what we use in all of computers. Every microcontroller has a lot of transistors for the ability to switch between states. Like essentially, transistors are capable of swapping between a Transistors are capable on given a potential input that to either let current pass through or not. And that is very fundamental to us making computers. Another things are like, yeah, transistors. For example, if I remember correctly, the new chips involve like in FETs we have, this is essentially a 2D thing. Uh, we have gates we have gates around and the thing flowing in between. If I remember correctly, this is a relatively new development where we have 3D gates, as in the we have a semiconductor thing in 3D, and then there's a gate in three of the, how do I draw it out? Like, I mean, definitely not like this, but how do I draw 3D? Okay, I'll just mark it like that. So we'll have a 3D gate instead of a 2D gate as here. These are these are new the technology is coming at the moment, and apparently that's even better than before. So I personally do not have a copy of Volten. However, I give me a second. Okay, so that will conclude today's class.